So today we're going to be talking about the chain rule. And well, sometimes in math you learn things that kind of fall to the wayside or you don't quite use them as often once you initially learn them. This is a critical concept in math and engineering and science moving forward. So if you plan on doing anything more with math or engineering, physics, whatever it may be, this is something that's going to pop up and you're going to need to know how to do. So let's get into it. So here you see the rule up here, and basically what it is it's used when you have a function nested inside of another function. All right, so that's what you can kind of see up here. Personally, I think it's easier to learn it by doing a bunch of examples rather than just memorizing the rule. So let's kind of look at some systems or some equations where the chain rule would be utilized. So here we've got e to the 6x, and you can see 6x is a function as well as e to the something. In this case, it's e to the 6x. That's also a function. So that's a function, 6x, nested inside of a bigger function. So we'd use chain rule for this. Another example, this might be a little easier to see. Here we've got x plus 81, so that's clearly a function, right? And then we've got that function, that whole function, raised to the 6th power. So that is another function. So that's a function within a function. Again, here, this is tangent of x, which is a function, and you're taking that function and you're squaring it. So again, the chain rule would be used here. Just a common misconception when people are learning this is that this isn't every single time that you see two equations together. Chain rule is only used when those are multiplied or like raised to a power, but not when they're added together. So here, like for example, you wouldn't use the chain rule in this because you would simply take the derivative of sine and add it to the derivative of this function, because this is only one function and this is only one function. They're not nested within each other. All right, so let's move into some examples. All right, so on to the first example. Here we can see we've got y equals the quantity of 3x plus 1 all squared. So first thing we're going to do is we're going to decide, do we need chain rule for this? And after taking a quick look, we see, all right, I've got a function here, 3x plus 1, and that function goes into another function, it's squared. So therefore we have this inner function, and then we've got an outer function of the first function squared. All right, so we've recognized there's a function nested in another function, so we need the chain rule, okay? All right, so now we'll actually start taking the derivative, and all right, so what we're going to do is first we're going to start with the innermost function. You always start with the innermost function, all right? And for us, that is this 3x plus 1, okay? And we can call it anything. Let's just call it f of x, all right? So f will equal 3x plus 1, all right? Because that's our innermost function. I'll put in blue here. 3x plus 1, our innermost function. Now what we're going to do is we're going to find the derivative of that, okay? So f prime equals, we're just going to take the derivative of this, right, which is simply 3, okay? All right, so now we're done with the inside function. Now we're going to move to the outside function, all right? So here we've got the outside function, which is simply this first function, which we called f, right? And it's f raised to the 2nd power. So let's call the second function g. And g, we decided, right, is just f, which is 3x plus 1, raised to the 2nd power, okay? So it's just f raised to the 2nd power, okay? So now, just like we did with the first one, same thing, all right? We're just going to take the derivative of it, okay? So g prime equals 2f, okay? Now we're taking the derivative with respect to f, all right? So now it's just 2f. All right, pretty easy stuff. Okay, so now we've got all the information we need. Now we're just putting it together, okay? So all we're going to do is we're going to start with the bottom right, okay? And this is obvious in this one, but when we're working with maybe F, G, H, I, J, K, you know, it's going to get a little more complicated. So we're starting with the derivative of the last row, okay, which is this G prime for us in this one. And we're going to take that and multiply it by everything above it, all right? So here we see G prime equals 2F, okay? So our answer is simply going to be 2F times 3, all right? However, right, F is just something we made up, okay? We said that F stands for 3x plus 1. So we actually have to plug in for F here. So this is the same as 2 times F, which is actually, and I'll write it in blue just to show that that's what we were calling it. So 2 times F, which is 3x plus 1, right? And it's just that times 3, okay? And if we wanted to simplify this more, we could just say, finally, that y prime equals 6 times 3x plus 1. All right, and that's the answer to our first chain rule problem. All right, so now we're moving on to another example. We can see right now, yes, we need chain rule for this because we've got a function, in this case, this nested within another function, which in this case is e to the something, okay? All right, so first we're going to recognize that the innermost function, which we see is just this 5x squared plus 7x minus 13. And remember, we can call it whatever, but we'll just call it f of x. And we'll say that equals 5x squared plus 7x minus 13. All right? So just like last time, we're going to take the derivative of that, okay? So we see f prime equals, and now this is just, you know, basic derivatives, you know. So 10x plus 7. All right, now we're done with that innermost function. So moving on to the next one, we see that the next function that contains the first function is this e to the f function. All right, so that we'll just call it g, and that just equals e to our first function right here. Okay, it just equals e to the f, or to the 5x squared plus 7x minus 13, right? So that's just e to the f. And now, just like we did in the last example, we'll just take the derivative, right? So g prime, and we know the derivative of e, e to the f would just be e to the f again. All right. So, okay, now we've got all the, now we've recognized all of the functions, we've taken the derivatives, now it's just time to plug stuff in, right? And utilize our equation. So, remember, just like last time, we're starting with the derivative of the last function. So that would just be this one right here, g prime. All right. So it'll just be e to the f, and it'll just be times everything that's above it over here. Okay. But remember, f is just something we made up to call this first function right here. Okay. So instead of plugging in e to the f, it's just really just e to this function. So it's e to the 5x squared plus 7x minus 13, all right? And then that's this. Now we just multiply it by everything above it, which in this case, the only function that's above it is this right here, which is times 10x plus 7, right? Okay, and that equals y prime, all right? So pretty standard, again, and now we're going to move on to maybe a little bit more difficult chain rule problems. All right, so moving on to a bit more difficult chain rule problems. We're going to see this one, which looks pretty intimidating, right? We've got a bunch of natural logs nested within each other. But the one thing you should remember about chain rule is really all it is just taking simple derivatives and then just using this equation to match them all up, right? So it's a lot simpler than you think, all right? So just be confident that you can solve this one. So first, obviously, it goes without saying, right? This is 4 times the natural log of the natural log of the natural log of secant of x, right? So clearly we need chain rule here. There's function upon function nested within each other, all right? So now, next step, let's find the innermost function, all right? So we can see that innermost function is simply secant of x, all right? And let's just call this f, all right? So f equals secant of x. Now, we're just going to take the derivative of that, all right? So the derivative of secant f prime is just secant x times the tangent of x. I believe that's right. Yeah, it is. Okay. All right, so moving on to our next function, right? So we're just seeing, even though there's a bunch of functions here, all we're doing is we're just going from the innermost function all the way to the outermost function step by step, okay? So what's the next one? The next one is just the natural log of this inner function, all right? So we'll call that g. G just equals the natural log of the inner function, which is just f, okay? So that's just natural log of f, all right? So now we know that the derivative of natural log is 1 over whatever it is. So here we get natural log of f. Derivative of g is just 1 over f. Continuing on, we're just trucking along, right? So we're finding the next function that that nests these previous functions. Okay, so we've already done this secant function, we've done this first natural log function, now we're on to this second natural log function. All right, so that we'll just call h. All right, and that's just the natural log of everything inside. And everything inside is actually just g, right? Because g is the natural log of secant of x. All right, so this is h would just be the natural log of g. All right, so moving over here, h prime, just like we did before, is just 1 over g. All right, so, all right, again, next step, we're just doing the exact same thing again. So what function nests all of these? We've done secant of x, we've done the first natural log of it, we've done another natural log, and now we're on to the outermost function, which is simply 4 times the natural log of everything inside of it. So we'll call that I, and I equals 4 times the natural log of everything in here, which is just h. All right, right, because h is natural log of the natural log of secant x. Okay, so we're just going to take the derivative of that, which is 4 times 1 over h. All right? So now we're done computing derivatives. All we're doing is we're going to just utilize the equation and plug things in, okay? All right, and one thing I want you to take note here is that even though there's this big scary equation that we have to differentiate, the only actual derivatives we did were just simple ones, right? Turning natural logs into 1 over f or 1 over g. You know, so it's not like there's anything crazy about this. It's just recognizing the pattern, figuring out which functions are within each other, and just knowing that you can do it. You can take on the problem. Okay, so in the last ones we were saying take the derivative. Start with the derivative of the last function, and we're going to do the same here, right? So we start with the derivative of the last function, which is I. Go over, take this derivative, okay? And we're going to start with that. So it's 4 times 1 over h. And I'm drawing it big like this, you'll see why. All right, so it's 4 times 1 over h. But h is not in this equation up here, right? H is just something we made up to take the place of the natural log of g. Okay, so we've just got to plug that in, right? We're going to plug in natural log of g for h, because we can't use h in our answer. It's not something from the equation. Okay, so natural log of g. But then the same thing goes with g, right? So g is something we made up too. So we got to plug in for g, which is the natural log of f, okay? So we're plugging that in, natural log of f, okay? Now one more time, we see, f is not something from up here. F is just something we made up to stand for secant of x, okay? All right, so we'll plug that in here. So f is actually secant of x, all right? And I think that's enough parentheses. Okay, so all that was we're writing this, right? This is 4 times 1 over h. It's just that h consists of many different kind of steps to find what it actually is, okay? All right, so now, just like we were doing in the other problems, we just take this last term and we multiply it by every term above it, okay? So we've got that now. That's our first term down here. Now we're multiplying it by h prime, okay? And h prime, right, is 1 over g. Now again, just like we were doing here, g is not something we can use. G is something that we made up. So we put g, we plug in for g, which is just the natural log of f. All right, and again, we can't use f, but we'll plug in for f, secant of x. All right. Okay, all right. So now we've done this, and we've done this. Now we're going up to this one. We got to multiply by that, which is just 1 over f. Okay, and again, right, you're catching on by now. We can't use f, okay? So we got to plug in for f, all right? Because f is just something we made up to call secant of x. So instead of having f equals secant of x, so we'll just plug in secant of x right there. All right, so we're done with this one. Okay, now we're just multiplying by the top term. Okay, and so this secant of x, tangent of x, is something we can use, right? That's a legitimate. It has actual variables that originated in the original function. We didn't just make up either of those. Okay, so now we'll just multiply this, and so I don't have to squeeze it in over there. I'll just multiply it on top of here times secant x tangent of x. All right. Okay, so and that's about it. All right, so that's our y prime equation. Okay, so notice that we really didn't take any crazy derivatives here, like I was saying earlier, right? This is all pretty elementary stuff. But what we did was we just recognized relationships, we utilized the rule, and we're able to get kind of a crazy answer, but a correct one from a difficult problem.